Today going to talk about how we are using two-dimensional materials to make devices for artificial intelligence. Artificial intelligence is all around us today. We are hearing of autonomous navigation, autonomous vehicles, so much about these cars. We are hearing about autonomous navigation in space. We are hearing about humanoid robots, which can do tasks which are hazardous for humans. We are hearing about robot soldiers and also in-home diagnostic tools which can help the elderly, which will monitor the body conditions continuously of people and will be able to report to the emergency room if something goes wrong. So many things are being developed these days, and we are looking at a very smart future. All good till we have this. So we all have digital assistant devices at home. Uh, and then when these, we are now very used to just shouting out voice commands, and the device flawlessly understands what we are saying and gives us the information that we want. All good till there is no internet at home, right? So when there is no internet connection, we cannot, these devices are becoming useless. So why is that so? Because these artificial intelligence devices that we see or use, they are too small to house the actual artificial intelligence circuitry. Because of the current way the artificial intelligence is operated, the circuitry that is required is so huge and bulky and power hungry that they have to be located in remote servers, which is the need for internet. So these devices have to connect to the internet to connect to those remote servers so that they can do the pattern recognition that is required. So what we are proposing is an alternative. We are trying to build the circuits so that they can be small, compact, and so that we can house them in these portable, very light devices as well. So for that, one of the outlooks is neuromorphic computing. What is neuromorphic computing? So currently we all know that we have the von Neumann architecture, where for the computers, the CPU and the memory are located in separate locations, and the data has to be shuttled between the CPU and the memory. So that's the von Neumann architecture. And computers are really, really good at computing, but not so good at pattern recognition. In contrast, our human brains, where the memory and the computing unit are not really separately located, they are co-located. Uh, our human brain is really, really good at pattern recognition tasks, and we can recognize patterns in a very small, short instant of time, and consume very low, and the brain consumes very low power in order to do so. The way the human brain is built, we know, is it has an interconnection of neurons and synapses. So billions of neurons connecting with trillions of synapses. So that's how the human brain is built. And the community is trying to look at at an alternative to von Neumann computing by following the way the brain is built. So instead of having the CPU, memory, and all the buses in between, we will the computer will be built, with basic blocks similar to the synapses and neurons of the brains. And different technologies are currently being explored to build such architecture. So this is neuromorphic computing, something which is emulating the human brain. Now, how does it work? Actually, neuromorphic computing, neural networks, which are based on the brain, have been there for a very, very long time, for decades now, but is implemented on software. So if you are, in this slide, I'm going to show you how the neuromorphic computing can be used for pattern recognition purposes simply. So let's say we have a letter to identify. So we are taking the picture of a letter and we want to identify that. How does it work? So here is an image of the letter H, and the image is broken into pixels. So here we have a 3 by 3 pixel, and then each pixel is attributed a voltage value depending on whether it is on or off, whether it is dark or bright. So the voltage value is depending on that. If it's a grayscale image, then it will have any value between 0 and 255. If it is dark, it is 0. If it is 255, if it is white, it is 255, and any color in between will be between 0 and 255, and things like that. So voltage values are attributed based on that on the color of the pixel. So we have to convert the pixels color to voltage values first. Then that voltage will have to be fed to this input neuron. So there is a series of neurons, and these are uh, so this is the start of the neural network, which is doing the pattern recognition. They are now being given input values based depending on the voltages. Now these will connect to the outputs by means of synaptic weights. So there's something called weights. So electrically, these are conductance values. So we have these weights connecting them. As you can see, all the neurons are connected to the next layer with these weights. And the next layer, what it is doing is summing up the entire current. So if you look at it, the V1 is voltage, W is conductance. So V1 times W1 is current. So we have now in this layer 3 neurons, these purple neurons, which are summing up the current through all these inputs. So we have that. Now this current, the total current, so what by finding out the total current, what have we done here? We have an input vector and we have a weight matrix vector, and these two vectors are multiplied. So vector matrix multiplication is taking place over here. And we know how computationally intensive that can be. So the software for pattern recognition, if you are talking in terms of software, there all these things are happening on software. So the image is coded to voltage. The voltage is now multiplied with the weight by vector matrix multiplication. The sum of the current is now going to be fed to the next layer, which is the activation function. These orange balls are all activation function. What is the role of that? Let's say that function will say that if my current is below a certain value, then I don't know what letter it is. If it is above a certain value, then I identify this letter as H. So let's say we are trying to identify Hij, we will say, okay, if this one's current is above a certain value, it's H. If this one's above a certain value, then it's Ji. If this one's above a certain value, then it is J. Okay, so this thing is the neural network. Now, if it has to be implemented in hardware, what is being done? Here is a row. We have this crossbar kind of a structure where we have this input line, as you can see the lines below, and then there is an active layer which is hidden from the picture right now, and we have perpendicular lines on top. So the voltage is being fed as the input, and we are at each of these cross points, the conductance of the material is being set. So we have now here the conductance. So if you are trying to get the current out of this line, we have actually multiplied V1 with the conductance. So the current, if we are taking out, is the sum of all these V1 times W1, 1 and so on. So just by taking the current from each of these lines, we are doing the complex function of vector matrix multiplication on hardware. Okay, so simple. Here, which the vector matrix multiplication on software, which is of O(n) squared complexity, that is getting simplified by realizing the whole vector matrix multiplication on hardware like this. So that's the first step. And then the current, now it will have to be fed into this orange ball, the transfer, the activation function, which simplistically could be a sigmoid function, where we say, okay, if the current is below a certain value, I don't identify anything. I don't know what it is, and if it is above a certain value, it's this particular letter, or it's this particular object. So
No,
that's how.
what happened?
So this is how the whole neural network will be realized on hardware. So what are the essential components? One is these synapses at each cross point. These are synapses, and the other is the neuron. So we have to build an interconnect. We have to interconnect these neurons and these synapses so that we can have the full neural network. And the neural network can have multiple layers like these. So if we are trying to realize many objects, then the neural network has to be even more dense. So they have to have multiple so-called hidden layers, which are again neurons connecting with each other through synapses, etc. So you can imagine that if we were to do it on software, then vector matrix multiplication has to be performed for every layer. And that happens, so when we are training the network, how do we do it? So for example, when we are training a child to identify, say, apple or orange, we have to show that same thing multiple times to the child. We say, apple, look at this apple multiple times, and then the child learns how to recognize the particular object. Similarly, for the neural network as well, we have to train it. We have to show the same thing multiple times so that the neural network gets trained to identify that particular object. So First of all, for every layer, we have to perform the vector matrix multiplication, and then we have these training epochs for which this whole vector matrix multiplication will be repeated. As a result of which, the training process is extremely computationally intensive and also time consuming if we are doing it on CMOS level. So now the if you're doing it on software level. So software is now running on conventional hardware, CMOS based hardware, made up of transistors. So these were never meant to operate like neurons and synapses, which is why the complexity today that we have to actually, the circuitry required is so bulky that we have to house it in remote servers. So it comes back to that story. Now all that can be cut short if we can use this crossbar synapses, and we are able to integrate these with neurons, and then the circuitry will be much, much lighter and can be housed in the small portable devices as well. Okay. So far what we have learned about is we need neurons and we need synapses. So first let me talk a little bit more about the synapses. For the synapse, what kind of device do we need? So the output characteristic will look something like this. We could plot conductance as a function of time. So let's say we apply 1 voltage pulse. So the conductance of the device is set at a certain value. We apply another voltage pulse, the conductance rises. Apply another one, it rises. Another one rises. Another one, it rises. So it is continuously rising. If we were to stop applying voltage pulses and we are supposed to just read what the conductance is, we will see finite of the same conductance as set by the last voltage pulse. So this is the retention of the device. So if we had withdrawn the pulses here, then also it should have retained the same conductance level. How do we bring back the conductance to its base state? We apply negative voltage pulses. So here it should be plus V, here we are applying minus V. And so this one is called potentiation, where we are seeing rising conductance, and this curve is called depression, where we are seeing falling conductance. So this particular curve where we are showing conductance as a function of pulse number or time, that's called conductance weight update of the synapse. And this is the single most important thing which is used by the neural network. So this is the curve which determines how nicely the synapse is going to get trained, how quickly, how efficiently, and how accurate the neural network will be. So yeah, what are the things that we require from this curve? As device people, we have to know this conductance weight update curve should show as high as possible the dynamic range, which is G max over G min. So highest conductance over lowest conductance. So G max over G min should be as high as possible, similar to the concept of on-off ratio. Oh, and then if you have that high on-off ratio, then you can also realize a large number of bits, large number of states will be there in between. So the bit resolution will also be higher. Then the other thing, which is nowadays considered very important, is the linearity of the weight update. How linearly is it going up and going down? How symmetric is it as a result of that? So these are important because now we are talking about more of online training, unsupervised learning, where the network has to be trained in situ in a dynamically changing environment. For that, linearity in weight update is extremely important. Okay, so now we know what we need from the synapse. So there are many kinds of synapse implementations so far. First one, I would just, for the sake of completion, I'll say it's CMOS based. So that's the most common one, where just because the transistors were never meant to behave like synapses, for a single synapse, we need multiple transistors. So it's a circuitry fully for one single synapse. So you can imagine to make a brain like system, you need many transistors. So if you have to make trillion synapses, you have to make even more transistors for that. So it's a very computation intensive process. It is a complex thing. And also you have to understand that if we are using synapse, then the vector matrix multiplication realization will be different. So that also increases the complexity. And the power consumption also increases accordingly. Then when in the early 2000s, the memristor, the missing memristor found paper was published. So the memristor was experimentally shown in an oxide-based system. RAM started to get developed resistive random access memory, because now we had a very simple structure, cross-point structure, metal insulator, metal structure, insulator being any kind of oxide over there. So that was showing switching because of temporary breakdown. And one was able to demonstrate multi-bit memory as well, resistive random access memory. It started with that. Then people started to also realize analog memory with these memristors. So then really good synapses started to be shown, demonstrated. And yes, a lot of papers still today exist based on these oxide-based synapses. But they have certain disadvantages. One is because this is a metal insulator metal system which is undergoing temporary breakdown. So that means the current through these devices will be really, really high. And that's difficult because now when you're using multiple synapses, the power consumption increases. And also there is another problem with these, that the linearity of the potentiation depression curves are not very good because of the processes involved. So the other system used to realize these synapses is phase change materials. Phase change materials are used because they undergo a phase change from amorphous to crystalline and back, and that causes change in conductance, and that is good for realizing synapses. Now, their disadvantages, yes, definitely high programming current, and the other one will be that the weight update curves are not very symmetric because there is an abrupt reset or abrupt depression associated with the physical process of phase change. Nowadays, 2D materials are being used to show these synapses. There's a lot of work shown here. So it initially started with using a PhET configuration. So a 3-terminal device was being used to realize the synapses. Because of the defects present, there was hysteresis that was being modified to multiple conductance states. So that was there, similar to the floating gate effect. Other mechanisms of synapses were also shown in PhET structures. Could be phase change, could be other mechanisms. Another, and then recently, people are showing metal, 2D material metal structures, which are also showing memristive effect. So the 2D material in between could be monolayer 2D materials, surprisingly enough, and also multi-layer insulators like boron nitride. So they are showing memristive behavior, which shows high prospect in using these devices as synapses. So we started with the idea of using a 2D heterostructure, primarily because we can very well anticipate that a two-dimensional material-based heterostructure, which is bonded by van der Waals attractions forces only, will have low interface trap density. And we saw that. We made a PhET out of 2D materials, and we saw with HBN with polysulfide as the channel and boron nitride as the gate dielectric. And when we performed CV measurements, we saw that very low dispersion, which was indicative of low trap density. We used conductance method to extract the trap densities, and we found that they are very good to numbers. We found really good numbers. The trap density at the 2D interface was 10 to the power 10 to 10 to the power 11, which is close which is similar in values to the silicon oxide and silicon high K interfaces. So with that thought that, okay, we'll get really very pristine interfaces, we wanted to use a graphene sulfide system as our synapse. So what would we do here? We used graphene as the bottom electrode, CVD-grown molybdenum disulfide as the active material, and we use, in this case, a metal as a top electrode. So yeah, everything is CVD-grown in these cases, large area, patternable with photolithography. So graphene was actually commercially purchased. Molybdenum disulfide we can grow in our own labs, and all are CVD-grown. And here, what do we observe? First, the DC characteristics. So here you see current versus voltage of this particular device, where we are seeing multiple conductance states. So when we clamp the current at certain values, we can see hysteresis, and then we see multiple conductance states, both in case of set, which is potentiation over here, and reset. And observable, noticeable things are that the operating currents are really low. So we have a very low off current and reasonably low on current here. So the operating currents are low, in low microampere ranges, in contrast to, say, oxide-based systems where the off current will be nanoamperes or high microamperes or low microamperes, and the on current will be in the milliampere ranges. So low on current is a low operating current was a positive, and also we can see the on-off ratio. So here the off current is in picoampere, and the maximum current we go up to is microampere. So we have a 6 orders of magnitude difference, which gives the prospect that this device can show good dynamic range. So when we pulse these devices, for number of reasons, we are not able to explore the full dynamic range, but still we are able to get a decent on-off ratio over here. And what we see is repeatable switching. This pulsing is showing these weight update characteristics repeatably being produced, and the weight update is also quite close to linear. Not completely linear yet, as you can see from the depression, but the potentiation looks quite linear. So that's what we see, and we establish the prospects of the system. Then we fine tune the structure a bit, thickness a bit, and we are able to now obtain a complete linearity and symmetry in the weight updates for 128 pulses. So we see 128 states over here because we are using 128 different pulses. And the linearity, as you can see over here, is close to 0, which shows ideal linearity. And that's why ideal symmetry as well. So this is just with the same graphene molysulfide structure, just the layers are fine-tuned a bit more. Then we see that, so in the last slide, we used 500 microsecond pulses. If we reduce the pulse width as well, still we can see, we reduce the pulse width, we can reduce the voltage amplitude, and we can still see linearity maintained. So we see repeatable linearity. So the characteristics can be linear for multiple input parameters. And the other thing here in this plot we are showing is the retention. So we are seeing so many different states, but are these states showing in retention characteristics? That is, for that we used actually DC to observe multiple conductance states here, and we are able to see good retention up to about 1000 seconds. So in this manner, we are able to establish a good quality synaptic device, electronic synapse. We move on to realizing artificial neurons now. So here our goal was to use the same active material as for the synapses. I'll talk more about the reason, but basically we want to make the neurons and the synapse using the same material system so that we can have monolithic integration. So in the past, we have seen neurons built with CMOS integrated with oxide-based synapses, which brings about heterogeneous integration, very complex, the yield becomes very low, and expensive processes. Or if we use different materials, so say phase change-based neuron versus oxide-based synapses, then it requires heterogeneous integration. Again, it's a complex process. So our idea was we'll use the same material system to make the neuron as well as the synapse. So for that, molysulfide is our active layer, and it's a little bit thicker in this case because of the device characteristics required, which I'm going to talk about in a second. And then we used silver as the electrode instead of graphene. And yeah, in the previous case, we used graphene as the electrode. We just use metallic bottom electrode, and we use silver as the top electrode because silver has a high diffusivity. For neuron, now, what are the device characteristics required? For neuron, the device has to be a threshold switching memristor, a volatile memristor. So here in this case, we can see that the memristor has is going from high resistance state to low resistance state at a particular threshold voltage, and it shows sharp switching. But in the reverse sweep, it goes back to its high resistance state. So it doesn't have a memory. So that's what is a threshold switching memristor. For neuron, I'll show you why again. We require a volatile device which shows sharp switching. So that's what we are able to obtain using silver as the top electrode, because as we are applying bias on the silver electrode, silver ions are diffusing into the molysulfide and are withdrawn as we apply a lower voltage, as we sweep the voltage backwards. We see sustained switching. This device has really good endurance as well, more than 10 to the power 6 cycles. So how to realize a neuron with it? So first let me show you what the neuron output characteristics should look like. If we are plotting current as a function of time, we should see spikes in time. So that's the neuron's behavior. This is called an integrate and fire neuron. So it fires, the current is seen in the form of spikes. How do we obtain that from that volatile switching memristor? For that, we need some circuitry to be attached. So we have an RC circuit attached to the threshold switching memristor. This resistance R naught is actually signifying the synaptic resistance. So synapse has a particular resistance. This R could be that synapse's resistance. And then we have C naught. C naught is actually the capacitor which integrates. So it's an integrate and fire circuit. So for that, this capacitor is the integrator. So how does this particular circuit show this firing characteristics? So first we apply voltage pulses at node A at the start of the circuit. When we're applying voltage pulses, in the beginning, this capacitor will start to get charged up. So this is the charging loop. Capacitor starts charging, and then the voltage at node B starts to increase from 0. So if it is increasing, at this stage, the threshold switching memristor's threshold voltage is not reached. If it is not reached, then it will stay in the off state, high resistance state. As the capacitor is getting charged, the voltage at node B will now increase, and when it reaches the threshold switching memristor's threshold value, then the memristor will turn on. So it goes to its low resistance state. So now what has happened is this loop gets activated. So now we have the capacitor charged enough so that V node B is higher than or equal to the threshold voltage value. And then this threshold switching memristor turns on. Then this discharging loop is activated. So the capacitor starts to discharge through the TSM device. When it starts to discharge, the voltage at node B will start to decrease. So now when it decreases below the value where the volatile switching memristor's memory is lost, right, it goes back to its high resistance state again. So again, this loop is open. So what happens as V node B? We see that it increases to the threshold value and then immediately starts to fall and go back to 0. And then again, integration happens. So the capacitor has to get charged up again. And then again, it increases to the V threshold and falls down, and so on and so forth. Because of this, the output at VRL, if we measured the voltage over here at this node, we see that the voltage will rise and then fall again, rise and fall again. And if we measure the current across this load resistor RL, we see this firing output. So we have the all or nothing firing, where we are seeing either the firing current or no current at all. So this is characteristic of the integrate and fire neuron. So this firing that we saw in time, it is a stochastic process. So every time it's not exactly the same number of input pulses required for a firing to occur. So if we plot a distribution of the number of spikes as a function of the number of pulses required for spiking, we see this distribution, which signifies the stochastic nature of a firing event. And that's a good thing, because in neural networks, people require a slight bit of stochasticity for convergence of the neural network. Otherwise, artificially noise has to be introduced. Then another thing is that the spiking, even though it is stochastic, follows a deterministic trend with respect to the pulse input parameters. So for example, if we increase the voltage, increase the pulse amplitude voltage, then the firing will increase. So that's what we see. So we plot number of spikes as a function of the input voltage pulse amplitude, and we see that the spiking has increased. And if we fit this data, we find that sigmoid curve. So this now can be used as the activation function of the neural network. So this is a good neuron because it is acting as the sigmoid function for the neural network. So that's what we see. And then we also see that if we change the input pulses duration, then the spiking will increase, because now wider pulses are being applied. As we are applying wider pulses, the spiking is increasing. If we increase the pulse interval, then the spiking will decrease deterministically. And then if we change the circuit parameter, so if we increase the capacitance value, then now the RC time constant has increased. So the time required for integration will increase. As a result, the number of spikes will decrease. And finally, if we change the C and R, both values, but keep C0 over R0 as a constant, then we see that the number of spikes is remaining constant. So here it is showing that all the characteristics of the neuron are being followed, the integrate and fine neuron, all or nothing spiking, and then pulse frequency, the spiking frequency is modulated with pulse amplitude and pulse input, pulse amplitude and pulse width and pulse duration, as the interval between pulses, and also circuit parameters like C naught and R naught. Now, the next thing that I'm going to show is a slight aside from the neural network parts. So the same threshold switching memristor can be used to emulate a biological pain receptor known as nociceptor. So nociceptor is a biological pain receptor which protects tissues from getting damaged. So what is the use of making nociceptor in circuits? Say, for example, you are making a humanoid robot. You can implant these nociceptors so that the humanoid robot's parts will not get damaged if there is an injury. So it can protect itself from accidents. So how does that work? So we have the threshold switching memristor. Here, if we look at the voltage versus time, then we see that as we increase the pulse's amplitude, input voltage pulse amplitude, the input current will also increase. If we increase the pulse width, then also the output current is going to increase. So these are characteristics of the nociceptor. And if we are to say, if we apply the same voltage pulse but a train of that, then what happens? It requires a certain amount of time for the device to turn on, and then when it has turned on, it maintains the same current level. And as we are increasing the pulse amplitude, we are seeing that that threshold, the time required for the device to turn on, will be moving towards lower and lower values, and the output current is increasing, but it's remaining steady at that constant value. So these are the characteristics of the nociceptor. There are two additional characteristics of a biological nociceptor called allodynia and hyperalgesia. So what happens here is, if the nociceptor is already stressed, so it has already been injured, how do we emulate that? Just by stressing the device. So we take the TSM device and we stress it at 2.5 volt or 3.5 volts. This is the injury condition. We find that now if you are applying a train of pulses, sorry, if you are applying increasing pulses of increasing amplitude, we find that the threshold has shifted to lower values. And another thing is that the output current also increases for the same voltage values. So these conditions are called hyperalgesia and allodynia, which are being followed by our nociceptor, pain receptor. So this device, just as an aside, can be used as a pain receptor as well, which can be used as a sensor system in a humanoid robot. So what next? Now we have a neuron and a synapse on this using the same material system. For monolithic integration, we built them on the same platform. So first we connected a single synapse with a single neuron, and here in the DC characteristics we are seeing that they are very well matched. So if we are sweeping the voltage, see the neuron switches, then the synapse switches, because this has a lower threshold than the synapse, and then then we have clamped the current at a certain value. So we see this, the current comes back, but then when we sweep again, and this time we clamp at a higher value, it actually first the neuron switches, and then the synapses current is dominating. So it is already remembering the last state. So that's what is happening. So we can see the individuality of the synapse and the neuron maintained, the volatile nature. And then when we use the synapse as the input resistance in the RC circuit connected to the threshold switching memristor, which will act as the neuron, we are able to see spiking behavior just as before, and the spiking can be well modulated by the voltage parameters, the pulse amplitude and the pulse width. And also, if we change the synapse's resistance, so if we increase the conductance, that is decrease the resistance, then the spiking is increasing. So that can be seen very easily. Then we connect three different synapses to one neuron here on the chip itself, same chip, it's laid out like that. And we can see that how the spiking frequency changes. So in one case, we have all the three synapses at the high resistance state, and then at a higher resistance actually. And then in state B, we have one synapse in in low resistance, two in high resistance. In state C, we have two in low resistance and one in high resistance. And in state D, we have all three in low resistance. So when we do that, we can see the spiking frequency is increasing because the overall resistance of the circuit is decreasing. So this is how we are able to show the initial part that we are able to now monolithically integrate the synapses and the neurons. Okay, so now I'm going to talk about a different device, which is the optoelectronic synapse. So in case of electronic synapse, we used voltage pulses as the input. Now in this case, we use optical pulse as the input. So when the device, the device has to be sensitive to light, much like a photodetector, but there is a little bit of difference, which I'm going to talk about now. So here in this case, we are shining light, we have the conductance, photoconductance. Next pulse of light, the conductance actually increases compared to the previous one. And with subsequent pulses of light keeps on increasing. If we were to withdraw the pulse of light, the conductance will be maintained at the same value. So in case of photodetector, what would have happened? If we apply a pulse of light, then the conductance will be increased. But as soon as we withdraw the pulse of light, the conductance will go back to the dark current. And with the next pulse, we'll reach the same old conductance. We'll not have increasing conductance. So that's the photodetector's part. However, due to the defects in the material, or due to the environment, certain materials show this persistent photoconductivity, which can be used to show increasing conductance with every pulse of light. So there is a memory effect inbuilt, or we can engineer the structure to show this effect as well. So how do we bring back the conductance? We can apply negative voltage pulses. So if we apply negative voltage pulses, we can bring down the conductance to its base value again. So this is an optoelectronic synapse. And what good is it? If you remember the pattern recognition circuitry, so there we said we have the image, the images, the pixel values will have to be converted to voltage using circuitry again, complex circuitry. Image processing has to be done. So that is now, because we are having the environment has so many things around it, right? So if, say, for example, somebody is trying to identify a car, there will be so many other things around. So, and if it is a dynamically changing environment, there is a lot of data. So now we require a lot of image processing and a lot of data to handle to convert the actual images information to voltage, and do a lot of and do the pattern recognition on it. So for that, it's so much easier if we can have the pixel itself being a part of the neural network. So here, if we have these optoelectronic synapses, now they can be part of the pixel. So each pixel consists of one optoelectronic synapse. So now when the image is being taken, the pulse of light, the conductance, the photoconductance is being set, right? So if it, instead of being a photodetector, now it has memory also. So now if we take the current out of these, the sum of the current, then we are performing vector matrix multiplication with this pixel array itself. We don't need to convert it to voltage and feed it again to the neural network. So this itself forms the part of the neural network because it has some memory effect. And then the same operations happen. We send the current through the activation function and we can recognize what digit or what letter, what object it is. So here in the hardware, we'll have the pixel arrays like here, and these cross points itself will be the pixels. And the same process. So we take the current out from each line, and that's doing the vector matrix multiplication, passing through the transfer function, and then we are able to identify the object. So what did we do towards that in that regard? We are using a graphene perovskite quantum dot structure first as a photodetector. So why graphene? Because graphene has high mobility, but by itself it has low absorption, low band gap. That's why, and it is not a great photodetector at all. But organic, inorganic halide perovskite, they are very good photodetectors in the sense they have high photoluminescence quantum year, but then they have poor charge transport. Mobility is very low. So what we did is we were able to grow these perovskite quantum dots directly on the graphene lattice. So it forms a superstructure. And then the perovskite quantum dot will absorb the light and it will generate electron hole pairs. That will be carried efficiently by the graphene. So using this structure, photodetector, we can get really good photodetection behavior. So photoresponsivity is extremely high, record high, specific detectivity is also very high. And then if we change the light intensity, we can see the Dirac point of the graphene shifting, which shows photogating effect. So it's a very good photodetector, which has photogating effect, all that. Now, if we apply a gate voltage, so this photodetection behavior is happening at a voltage of 0 volt. If we apply a series of optical pulses and change the gate voltage to more positive values, now we can see the potentiation behavior, and then also the conductance state after a slight relaxation is retained. So here, by applying positive voltage, we are able to trap carriers of one type and cause this behavior. So again, we can do light-induced potentiation and electrical pulse-induced depression as well. However, because this is a graphene-based system, the dark current will always be very high. So that's not a very desirable picture. So we want something with the band gap so that we can have low dark current, and molybdenum disulfide is a very good example. It's so we use monolayer molybdenum disulfide grown by CVD, and when we shine light, we see enhanced current as is expected, and also we can see increased photoconductance with increasing intensity. All that is good. So these are more or less in the same line as making a photodetector using molybdenum disulfide, which has been shown for a very long time now. But when we are again applying gate voltage, in this case, we're applying negative gate voltage, what we observe is again the potentiation and then retention of the conductance state. And for high enough negative gate voltage, we are seeing here retention of more than 10 to the power 4 seconds here. So why so this is happening because of again the persistent photoconductivity in MOS2. So I don't show it here, but we have used different substrates. We have used aluminum oxide as the backgate or silicon dioxide as the backgate. We have measured in vacuum, in air. We have measured on exfoliated versus CVD, and all of them show this characteristic because of the inherent defects which are present in molybdenum disulfide. But instead, if we use tungsten selenide, we don't see this behavior. We see the behavior of a photodetector. So the current goes down to the dark current as soon as light is switched off. So some synaptic characteristics need to be shown. So one thing is paired pulse facilitation, PPF. What happens is that this tests the effect of, if we are applying two pulses, then it tests the effect of the second pulse, effect of the first pulse on the second pulse. So if the two pulses are far away in time, then the first pulse's effect will decay, basically. So that's the idea. So we show that paired pulse facilitation. We show optical potentiation, electrical depression. Here we are applying negative voltages at the drain to detrap the carriers and go back to the initial dark current value. Okay, so before I end, I'm going to talk about a slightly different work that we were doing, which is on solar cells. And this is on ultra-thin solar cells, and we are doing some light trapping on them. Now, first of all, why do we need ultra-thin solar cells? Because one thing is that nowadays you want energy harvesting device for whatever electronics we are wearing, smartwatch or phone or etc. For that, we need to have a flexible energy harvesting device because of the wearability of it. And also because it will be lightweight, also will save material cost. That's why we want flexible ultra-thin materials to make solar cells. However, the disadvantage is that a thin substrate will absorb way less light than a thick substrate. So as a result of low light absorption, there will be low efficiency. So what is done as a result? One uses plasmonics, so where metal nanoparticles can be used as plasmonic structures, but the problem is that the absorption increases, but due to them being metal, the heat dissipation is high. So the optical gain is offset by electrical loss. Another way is using bio-inspired schemes like the moth eye, where silicon nanopillars have to be made, but this is, as you can see from the picture over here, it's quite complex, right? For solar cells, we want the process to also be very cheap. So what we thought of is the leaf has evolved to maximize the absorption of light. And how it does so is by its cells. So it has the palisade mesophyll cells, the upper epidermis and the palisade mesophyll. They have the function of focusing and funneling the light. They behave like waveguides. And the spongy mesophyll cells, their work is to scatter that light to the chloroplasts. So what we wanted to do is we wanted to use this kind of a scheme on our solar cells. Here we are doing it by means of nanoparticles. So what will happen here? We have this larger nanoparticles and we have this smaller nanoparticles. The larger nanoparticle will waveguide the light. How? The light will fall on it, and then there will be total internal reflection, and because of the refractive index mismatch between the air outside and the nanoparticles refractive index, which is higher than air's. So when it is getting trapped in this way, it is forming whispering gallery modes. Now this can only leak light to the lower layer, which has a higher refractive index. So here is the only escape path. The light leaks to the lower layer. This has a higher refractive index. And then these are small and they will be able to scatter the light efficiently to the underlying substrate. So how do we realize this? We use an all-dielectric light trapping scheme because we want it to be lossless. We don't want the heating effects to be there, and we don't want the optical gain to be compromised by the electrical loss. And for that, we want to also use a very cost-effective, easy way of realizing it. We use the Stober process to synthesize these nanoparticles and then just spin coat these nanoparticles on the substrate. So for demonstration, we used an ultra-thin graphene silicon solar cell. So silicon is about 20 micron thick over here, and the graphene layer is a monolayer. So, or actually it's a bilayer. So this is a very thin structure. It's flexible, as you can see from this picture over here. And this is a Schottky junction solar cell. It's not a PN junction solar cell because graphene acts like a metal on silicon, P-type silicon. So here we have spin coated the titania and silica nanoparticles. So we use the smaller nanoparticles made of titanium oxide, and the larger nanoparticles are made of silica. So because of the refractive indices of the two. Then we realized with simulations that the ratio of the diameters of the silica and the titanium nanoparticles is extremely crucial for light trapping. So we performed simulations and found that the optimized dimension is 6:1. So the dimension of the larger nanoparticles should be 6 times higher than the dimension of the smaller nanoparticles. And then 600 nanometers is the diameter of the larger one. And that's a good thing because it matches with the wavelength of the light to be trapped. And this diameter of the smaller nanoparticle should be much smaller than the wavelength of the light so that it can be efficiently scattered. So here in simulation, we see that using these particular dimensions, we can get the whispering gallery modes, the leaky modes, and then eventual scattering of light to the underlying substrate. So on the solar cell, when we demonstrate this light trapping scheme, we see very drastic reduction of the reflectance. So reflectance of bare silicon substrate with graphene would be about 28%. Now it has gone down to 10% reflectance. And sorry, 10% reflectance, sorry. So the reflectance has reduced, and when we are measuring the IV of the graphene silicon solar cell device, we see enhancement in efficiency by means of enhancement in short circuit current density. VOC remains the same because we are actually not doing anything to the band structure or to the traps there. So only or recombination lifetime. So only thing which is increasing is the short circuit current density because there is higher absorption by the light trapping scheme. So we see a 30% increase in efficiency due to the light trapping, and we also do the pseudo JV characteristics because the Schottky junction solar cell is also contact limited. So there also we see similar enhancement in the efficiency because of adding the light trapping scheme. Then because of using spheres as the light trapping thing, we see omnidirectionality in the light trapping. So the sun is going at various angles throughout the day, throughout the year. So omnidirectionality is a very desirable quality in any kind of solar cell. And as you can compare, if you compare with the moth eye, since they are nanopillars, the omnidirectionality is not maintained. Here, since we have a sphere, any angle of incidence will have the same effect on the light trapping. So the light can be trapped even with any angle of incidence on the device. So that's what we see experimentally as well. Then the flexibility we can study, we actually make the radius of curvature or 3 millimeter, 20 millimeter to down to 3 millimeter, and we can see extremely good characteristics up to 1000 cycles. So the same efficiency is maintained. So finally, to summarize, I showed you the graphene molysulfide artificial synapses, which with near linear to linear weight update. I showed neurons using molysulfide using silver electrodes, and then I introduced you to optoelectronic synapses with graphene PQD superstructures and monolayer molysulfide, and then I digressed a little bit to show you some ultra thin graphene silicon solar cells where we use a bilayer light trapping scheme to increase the absorption, hence efficiency, by about 30%. I have to thank my team because they did all the work. So this is a little bit older picture of the team. So right now I have about 5 graduate students. Most the work were done by my postdoc, Dr. Sonali Das, graduate student Aditi Durjoy, and Manshul. I have to acknowledge my funding sources, NSF CAREER Award and Air Force Research Laboratory, Ball Aerospace BA Systems, and UCF Foundation for their support. And thank you very much for listening.
Okay, great. Thank you.
Thank you. Let's see the questions. Sorry, I could not look at the chats.
Okay, that's all right.
So would you like to read the question out and answer them, or do you want me to read it out? Which way would you prefer?
Okay, I can start reading. So I'll go according to the chats.
Sure.
So first question is by you, Sriram. Is that gate voltage or drain voltage? Potentiation? Yeah, it's all drain because it's not a gated device. It's a 2-terminal device. So that's the gate voltage.
Okay.
Then
that's for the synapse, right? Yeah.
Yeah. Mm-hmm. For the electronic device, electronic synapse.
Sure.
Then Arka Bhattacharya is asking 2 questions. One is, why is 2D material most attractive for this purpose? So I'm guessing you are talking, well, from the next, are you talking about synapses or
yeah, synapses.
Well, I cannot say it is most attractive right from the onset, but first of all, because of the thickness of the structures, it is, we found many desirable qualities. And as we are testing it more and more papers are getting published, actually, we are seeing that the cycle to cycle variation is very, very low in these devices. A lot of reports are coming out. So it is turning out to be very lucrative, but I don't think it started with that idea. As things are getting discovered more and more, a lot of good qualities are coming out. But if we started with the idea that, okay, the interfaces will be really good, and then the breakdown mechanism should be a little bit different, at least from how oxide was behaving earlier. So with those things in mind, it was coming out to be more attractive. And then the thickness levels, let's say, people saw switching in just a monolayer, which is 0.7 nanometer of 2-dimensional material, which is not possible if you put.
So maybe then also the voltage ranges required for these phenomenons is much more. I mean, it's low power when you deal with 2D systems. Is that?
Actually, voltage ranges are comparable with oxides somehow.
Okay.
Yeah. Then Arka asked the second question, does having high DIT severely affect the linearity of the conductance versus time plots in these 2D material FETs? Well, high DIT, I think there is lower DIT in these devices. One, does that affect the linearity of the conductance? So the linearity will be coming mostly from the way the conduction is happening. So one can actually assume that in the 2-dimensional material, it is not really breaking down per se, right? Like oxide, the conductance will happen, conduction is happening because it is going through that temporary breakdown. So because of that, the conductance, the linearity could be different. There is actually still no comprehensive study showing why it is showing more linear than other systems. So that part is still open. Or the repeatability of pulsed performance is affected. It doesn't. So I think one of the factors would be that the interfaces are also very clean. So if we were to have conduction in these switching devices could be either more based on interfaces, or it could be based on filaments, conductive filaments. So one way or the other, say there is a high chance, again, there is no solid proof yet because it's a comparatively novel field, not many people are working on it. The conduction in these devices could be interface mediated. So in that case, the process might be much more controllable because we already have a very low amount of traps to start with. So that's there. So people are seeing more linear behavior in 2-dimensional based memristive systems. Then Rujun Sun is asking, will gallium oxide be suitable for artificial neuron applications? In other words, what are the principles to select materials for artificial neuron? Yeah, the principle, the material, more than that, I think the electrode makes a good reason for better case than the material itself. Usually people choose electrodes which are made of high diffusivity metal, so either copper or silver, so that if you apply a slight voltage, the ions can diffuse into the material and you can pull it back with the application of opposite kind of voltage.
Would you want like some like material with a high open volume or something, like diffusivity of these metals
Yes,
higher?
yes.
Yeah. Okay.
Yeah, as long so if you have a higher diffusivity in a particular material, that also might be helpful. But we have to make sure that the conductance path is not very stable, because if it is too stable, then the device will become non-volatile. So then it becomes a synapse. So gallium oxide, I don't know whether the diffusivity will be higher or lower. Maybe Sriram, you can say better about that.
I have no idea.
Yeah. Okay. Oh, Shriram, again, you're asking, could you please comment on mechanism or current understanding, okay, behind memristive behavior? So one thing is that I would still say it is a mix of interface mediated and conductive filament. So a lot of papers are coming out which is showing conductive filament. And there is one paper which is showing it's actually the diffusion. So in monolayer molysulfide, if we say what kind of switching is happening, first of all, it's strange that just a monolayer will show switching in the vertical direction. It has been shown through STM and TM that they use gold electrode, and the gold add atoms are causing the switching. So that's a recent paper in this year.
So it's
No,
almost
sorry,
like you're
2020.
controlling the amount of electrical short.
Yeah, yeah.
Okay.
Yeah. So that's about that was a very recent paper. Other than that, conductive filaments are being seen in these devices, which will be very similar to how oxides even work, right? But then, because if we have a 2D 2D interface versus even a metal 2D interface, that can also act as the reason for switching in these materials. A lot of work is going on as well to show what is the mechanism. Okay. So Steve, yeah. Many more questions have come right after that. If Veilu Gao says, if defect grain boundary is the reason for creating memristor, what would be the approach for large-scale circuits? Is there any way of precisely controlling those defects grain boundary in large scale? So that's one of the hypotheses. So one paper was published and made many follow-ups from there, where they said grain boundary is the reason for switching in these materials. So yeah, that's right. So if we have a large scale circuit, and if you are moving towards a field where you don't want to have so many grain boundaries in the material system, what will happen in that case? So that's an open-ended question. But then, yeah, definitely in any switching, in any memristor system which is switching, defects are the reason for that, right? Already some defects are present, and by application of field, you're aligning the defect so that the conductive filament gets formed. So that's how oxide-based memristors are working. So in 2D materials, also we can believe the same thing might be happening, because there are lots of sulfur vacancies. CVD-grown materials, sulfur vacancies will abound. And by applying an electric field, you're aligning those, which is causing the filaments to be formed. So as far as grain boundary is there, I don't have too much comment, because people, yeah, sorry, I don't have much to comment about. So a grain boundary, if it is a reason for switching, that's one of the hypotheses. And more studies are required to go in that direction. Okay, then Stephen is asking, how accurate is the image identification using the MOS2 synapses, and is there a difference in convergence rate of the neural network using these synapses in comparison to other synapses? So far, actually, yeah, so if we use the standard neural networks available, open source neural networks, when we have used our parameters on the devices, we actually see the one of the highest accuracies reported with these new emerging devices. So if we are comparing with oxide-based or amorphous silicon-based devices, we can see that our devices show really much higher accuracy. And because of the higher on-off ratio, the accuracy and the epochs required to come to that accuracy is higher. So right now, if others are giving, say, 70%, we can get 80% and above. So that's the kind of range. But so it's again simulation. We have not made hardware based neural network yet. Then Arka is asking. Wait, sorry, it just slipped. How accurate is the image identification using? Sorry. Arka is asking: is the larger nanoparticle, smaller nanoparticle scheme addressing the ease of fabrication or performing enhancement compared to nanopillar or recently studied nanofunnel structures? All of them. So all of the above. So first of all, one is definitely ease of fabrication, but also the omnidirectionality, right? That would not be there in if you have a cylindrical structure, pillar-like structure. So omnidirectionality is addressed by the nanoparticle because we get it, any angle of incidence, oblique or direct, would cause the same amount of enhancement. Also, I didn't talk about it, the polarization, it's also polarization independent. It's there in the paper. We don't talk about, I didn't talk about it in the presentation. So the nanoparticles scheme, whether it is transverse TE polarized or TM polarized, still it gives the same performance. So that was the good part. There are several advantages actually. So yeah. I think that's a lot of questions.
That's a
Thank
lot
you
of
very
questions,
much.
and
yeah,
that was an outstanding seminar. It just blew my mind, and you covered a lot of things. And I learned a lot today. Thanks for your time, and thanks for the students who stayed on and asked these interesting questions.